So this is the general form of a linear system. In terms of scalars, we have a1 1x1 plus a1 2x2 dot dot a1 and xn equals b1. That's the first row, and am1 x1 plus am2 x2 dot dot amn xn equals bm. That's the last row, the mth row, and the ith row is as follows: ai1x1 plus ai2x2 plus dot 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 ainxn equals bi, or we can write it the ith row in this form: summation j aij xj equals bi. So this is an overdetermined system when m is greater than n. So we have more equations than the number of variables, in which case we cannot get an exact solution. Therefore, we seek an approximate solution that minimizes something. On the other hand, this is an underdetermined system when m is less than n, so we have less equations and a more number of variables. So this is what it looks like. So here we have an infinite number of solutions, x, and so we select the one that minimizes something. So this is the general situation in terms of vectors and matrices. Ax equals b is what we want to solve. And the solution, the general solution, is x equals a pseudo-inverse b. A plus is the pseudo-inverse of the matrix A. Now, when A is a tall matrix, that is, m is greater than n, then we are looking at an approximate solution that minimizes the sum squared error. This is the expression for the pseudo-inverse of the tall matrix. We will assume that the rank of A is n, the minimum of the two dimensions m and n, and in which case A transpose A is invertible. Now, when m is less than n, then the matrix A is a wide matrix, and we will assume that it has full row rank m. The solution is the exact solution that minimizes the squared norm, x equals a pseudo-inverse b, where a pseudo-inverse is given by this expression now, and like I said, the rank of A is m, in which case A transpose is invertible. So this is graphically what it looks like for an overdetermined system. Since we cannot satisfy all m equations using n lesser number of variables, so we seek an approximate solution. So that's why I have Ax is approximately equal to b, and define the error between the LHS and the RHS as R equals b minus Ax. The min norm solution is the one that minimizes the L2 norm squared of R, that is R transpose R. So X star equals argmin R transpose R, which is argmin of b minus Ax L2 norm squared. And this is the expression for the pseudo-inverse. A plus is A transpose A inverse A transpose, and our solution is X star equals A pseudo-inverse B. And graphically, this is situation. A transpose A equals this small matrix here, and it's invertible. So A pseudo-inverse A equals the identity matrix. On the other hand, A pseudo-inverse cannot be the identity matrix because this A pseudo-inverse will not be of full rank. In the underdetermined situation case, this is what it looks like visually, and we have an infinite number of solutions. So we choose the one which has the minimum length. In other words, we want the min norm solution x star, which minimizes the L2 norm squared of x. This is the solution x star equals A pseudo inverse B, where A pseudo inverse is given by this expression now. Now we can see that A transpose is invertible. And it can be shown that A pseudo inverse is the identity matrix. But A pseudo inverse A can never be the identity matrix because A pseudo inverse A is not even of full rank.